Okay, so last time we started talking about extended surfaces, and I guess some of the key points that I hope you got out of last lecture was, first of all, what the extended surface approximation is, how it's basically this idea that in some problems, the resistance to conduction in some direction is so small that you can neglect it. You can throw it away as being small so that there's no temperature gradients in that direction, and therefore you've reduced the dimensionality of your problem, right? So this was the specific problem we were talking about. We said in this fin, temperature varies both in x and in y, but if the resistance to conduction in y is small enough, then I can approximate the temperature as being only a function of x, and that's the extended surface approximation. It's justified with what we call a BO number, which is a dimensionless number. That's the ratio of the resistance to conduction in the direction that we want to neglect. So in this case, in the y direction, divided by the resistance from the surface to the surroundings. So in this case, our convection. And we went ahead then and made the extended surface approximation and analyzed this fin, and so that gave us an ordinary differential equation, which we solved, and here's the solution right here. We looked at the solution. Before we sort of move on from this, I think it's worth talking about how we would use this solution, right? Because this is a fin, and fins are kind of ubiquitous in heat transfer devices. You see fins in almost any heat exchanger or heat transfer device you want to pick up. So the way that you use this temperature distribution in this kind of a situation is you use it to calculate the rate of heat transfer to the fin, because that's really what you're after. I mean, if you notice, the boundary condition that we had for this problem was here at the base, we had a base temperature, right? So that temperature tells us nothing about the rate of heat transfer to the fin, right? This is definitely not adiabatic. It's basically saying if I specify a base temperature, the heat transfer rate is whatever it needs to be to keep that base temperature, right? So I would like to now know what is the rate of heat transfer to the fin. And there's two ways of doing this, I guess. If you think about drawing a control volume around the fin, because I'm at steady state, for this control volume, in has to equal out. There's no stored. So what's going in is the rate of heat transfer by conduction here at the base of the fin. And what's going out would be convection from the surface. So those two things have to be equal to one another. And I could calculate the rate of heat transfer either to or from the fin using either of these two techniques. If I want the rate of heat transfer by conduction to the base, then I would use Fourier's law here, evaluated at x equals 0, right? And that's what I get here. I would just take this temperature distribution and plug it in here at x equals 0. If I want the heat transfer rate by convection, now I would have to integrate the rate of heat transfer by convection all the way along the fin. So q dot fin is q dot convection, which is the integral from 0 to L of h bar times the perimeter times t minus t infinity times dx, right? So if this solution is correct, then this equation and this equation had better give me the same thing, right? So I can use either one of those two techniques to get the rate of heat transfer to the fin. I'm going to do the first one here. So let's go ahead and do that. Here's q dot fin evaluated using conduction at x equals 0. So I'm going to take this temperature distribution, plop it in here, take the derivative, and then evaluate that derivative at x equals 0. So here's taking the derivative. Let's see. The derivative of a constant is 0, so that goes away. And then I have tb minus t infinity times the cosh of mx. So that would be tb minus t infinity times m times the sinh of mx, right? Evaluated at x equals 0. And then here I have tb minus t infinity times the hyperbolic tangent of m times L. And then sinh becomes m times cosh, right? And the sinh at 0 is 0, so this whole term goes away. The cosh of 0 is 1, so this becomes what I've got right here. And just to remember, the m here is the square root of the perimeter times h bar over KAC. So if I substitute that into here, I get this equation here, which makes sense to me, I think, right? The rate of heat transfer to the fin definitely ought to increase with TB minus T infinity, right? The temperature at the base minus T infinity, that would make sense. If the fin becomes more conductive, heat transfer goes up. If there's more cross-sectional area for conduction, heat transfer goes up. If the heat transfer coefficient goes up, the heat transfer rate goes up. And then if there's more perimeter exposed to the fluid, the heat transfer rate goes up. So at least in terms of how this varies with these parameters, that makes a lot of sense. Typically, this solution right here is recorded in the form of what we call a fin efficiency, right? So a fin efficiency is a number between 0 and 100%, and it basically just tells you how good is your fin relative to the best possible fin, right? So typically in a situation like that, the hard part is figuring out what is the best possible fin, right? What makes sense to put in the denominator of this equation. In this case, the best possible fin is chosen to be a fin that has a conductivity going towards infinity, right? So I've made my fin out of the most conductive material that I can possibly find. And if you think about what the temperature distribution looks like in such a fin, basically I'm up here at this ml equals 0 limit, right? So if you think about what it means for the thermal conductivity to approach infinity, that means that your conduction resistance in the x direction has become 0, right? So you can move energy along the fin conductively with no penalty at all. You have no temperature drop, and that's what this upper line is. So that is a case where your fin everywhere along its surface is at the base temperature because there's no temperature drop due to conduction. So the entire fin, all the way from the base to the tip, is all at the base temperature, right? And in that limit, then, this is just a convection problem, right? The only resistance left is that convection resistance. You just take the surface area of the fin, multiply it by h bar, and then by TB minus T infinity, and that is the rate of heat transfer that you would get from your fin if you truly could make it out of an infinitely conductive material. So that's what goes in the denominator here. And this is, just to be clear, the definition for any fin, right? So this definition of the fin efficiency you would use for any fin, and there's all different types of fins in terms of shapes and even boundary conditions and things like that. No matter what the shape of the fin is, this is the definition that you would use to define a fin efficiency. We just got done going through and solving a problem related to a very specific fin, and that's a fin that has a constant cross-sectional area and an adiabatic tip, right? So for this very specific, actually very simple fin, this is the solution that we came up with, right? So if I want to know the fin efficiency for this particular case, I could just take this equation here and put it in the numerator, and then I have to figure out what to put in the denominator. So in the denominator, I have h bar times the area of the fin that's exposed to the fluid times TB minus T infinity. So if I go back here and think about this fin, the area of this fin that's exposed to the fluid is simply its perimeter times its length, right? We're not going to count the tip because this is an adiabatic tip fin, and therefore the tip is not exposed to the fluid. So I would use here h bar times the perimeter times the length times TB minus T infinity. So if I plug that into the top and this into the bottom, here's my fin efficiency solution for this particular problem, right? And I can simplify this in some obvious ways. I can cross out TB minus T infinity, and then I'm left with this. If I do a little bit of algebra with this, so pull the h bar times perimeter into the square root, I get this. And if you look at this right here for a little bit, you realize that this is just 1 over m. So this is my fin efficiency function for this particular case, right? It's the hyperbolic tangent of m times L divided by m times L. So if I plot the fin efficiency as a function of this m times L fin constant, it looks like this. If you think just for a couple seconds about, again, what m times L is, if you remember, here we can go back and look at this plot, this ML parameter is really the ratio of R conduction in the X direction to R convection, right? So when ML gets very, very small, I'm moving towards that ideal fin, right? And sure enough, I'm moving towards a fin efficiency of 100%. What my fin actually does, and what the isothermal fin would do are the same thing, right? So 100%. And then as ML gets bigger and bigger, of course, my fin efficiency suffers because of that conduction resistance not being 0 anymore. All right, so that's the fin efficiency. Obviously, fins have been around for a long time. They come in all different flavors. You can look in different books and find tables that look like this one. So for these different possibilities of fin shapes, you have your own or a unique fin efficiency solution over here, right? These are also tabulated in ease, actually these and many more. So let me just show you where to find these. If you go to ease, so let's see if I can find ease. So here's ease. If you go to options, function information, and you go to the heat transfer and fluid flow library, one of these ought to be fin efficiency. So that's what this one is right here. You'll notice you have two solutions here, or two options here. You can have a dimensional efficiency and a non-dimensional efficiency, right? So a non-dimensional efficiency would be where you give it, in this case, just m times L, right? That's a dimensionless number, so this is my non-dimensional efficiency. If I call the dimensional version of this, I have to give it a whole bunch of dimensional quantities. And of course, all this does then is use these dimensional quantities to calculate m times L and then call this function here, right? So it's just saving you the time to do that. If you look through these guys, you'll see there's a whole bunch of different options for fin shapes. And you can use these to calculate the fin efficiency for each shape. I will point out that you also need the fin area to use this effectively. And if you choose information, this is probably not the best one to look at. Let's look at this one here. So if you choose information, there should be an equation here that tells you how to compute the fin area, the surface area, which is something you'll need as soon as you start to use this this solution. Okay, one last word about fins, and that is that you can use what's called a fin resistance to now take this fin solution and incorporate it into other problems or problems that involve other heat transfer mechanisms, right? So if you look at this equation here for the fin efficiency, and you just solve for Q dot fin, you get this equation here, right? Q dot fin is eta fin times this part of the equation is the heat transfer from the ideal fin. And if you stare at that for a couple seconds, you realize that this looks again like just another resistance equation, right? The resistance of a fin is the inverse of this stuff here, right? The rate of heat transfer from a fin is driven by TB minus T infinity, and then the resistance is 1 over this stuff here. So R fin is 1 over eta fin times H bar times AS fin. This is interesting if you look at it. This is saying that basically a fin resistance is got the same form as a convective resistance. Remember, the convection resistance is 1 over H bar times the surface area. But I have this fin efficiency that sits down here. And the fin efficiency is always less than 1. So it's saying that this resistance is always going to be bigger than what it would be if it were just a convection resistance, right? And that increase is related to our conduction in the X direction, right? It's related to the other resistance that sits inside of this solution that impedes heat transfer as you have to move it along the fin, right, to have it be convected. If the fin efficiency is 100%, then I limit back down to just being a convection resistance, which is exactly what that ideal fin is. But as the fin efficiency drops, I have more resistance than I would get if I were just including convection resistance. So if I have a problem like this, where I have some kind of fin surface area, right? I have a whole bunch of fins, but maybe I also have, some region of a base that isn't covered with fins. I can now sort of construct a model where each of these fins is represented by a resistance, And then, other things are represented by other resistances. So in this case, the unfinned region is represented by another resistance. And I can put it together and, think about larger problems in which the fins are incorporated into that problem by virtue of these fin resistances. And these fin resistances, of course, use these fin efficiencies. Okay, that's fins. I guess the next thing I'd like to talk about in this lecture is extended surfaces that are maybe just a little bit more complicated, right? So we just did an extended surface problem where we had a constant cross-sectional area fin, constant perimeter, and we got an ODE that hopefully you've seen before, right? It wasn't very difficult to solve. Let's do a fin now that is a little bit more complicated in that as I move along the fin, the cross-sectional area actually changes, and so does the perimeter. And that kind of fin is shown here. At least one example of that kind of fin is shown here. This is a pretty typical thing you might see where you have a tube, and on the outside surface of the tube, you've installed these annular sort of washer-shaped fins, right? So imagine a disc, right? So this is sometimes called a fin tube. You wouldn't just see one of these fins, every so often on the tube, you'd have one of these fins kind of sticking out, right? So they show up kind of a lot. It'd be nice to have a solution to this, and of course there is one, but we can try to understand where that solution comes from and come up with the solution ourselves.